All right, so here we go with our test review. Unit 4, empirical formulas, molecular formulas, hydrates, some percentages. So a 350 gram sample of iron ore. Iron ore means the rock from which the iron is mined, and it weighs 350 grams. So the iron plus the rest of the stuff, so that would be the whole. 63.5 grams would be the part. So the way we're doing percentages is part over the whole times 100. So the part, because of iron, is 63.5 grams. The whole thing weighs 350 grams. So divide those two and then multiply by 100. You could also do it as a ratio. 63.5 grams is to 350 as x is to 100. So when you're doing a percent, it's always x is to 100. 63.5 divided by 350 times 100. And the answer is 18.1% iron. So that particular iron ore is 18.1% iron. The second question is, it's only economical to mine it if it's at least 20%. Should they do it? Well, the answer to that would be no, because if it has to be 20, 20 is greater than 18.1, and so you would not want to mine that ore. All right, second question. Percentage composition means find the percent of each element. So in that particular substance, we have sodium, we have carbon, and we have oxygen. So we want to find the percentage of each of those. So the process is find the mass of the whole thing. So we have 2 NAs, 1 carbon, 3 oxygens, 46, 12, 48. So 106. So the molar mass of that particular substance is 106. So the percentage of sodium equals. So we do the same thing we did in that first question. Part over the whole times 100. So the part of sodium is 46. The whole thing has a mass of 106. And then times 100. Or once again, you could do it as a ratio. 46 is to 106 as x is to 100. Percentage of carbon then would be 12 over 106. And the percentage of oxygen would be 48, 106. So we just basically divide 46 divided by 106 times 100. We got 43.4%. 12 divided by 106. We got 11.3%. 48 divided by 106. We got 45.3%. So there's our percentages. And again, percent composition means you're going to find the percent of each element. All right, now the second part of this is how many grams of carbon are there in 27 grams of the substance? So now we're saying if you have 27.8 grams of Na2CO3, the question is how many of those grams are carbon? So out of that 27.8 grams, how many grams are carbon? Well, in the previous problem, we figured out that it's 11% carbon. So we would just take 11.3% of 27.8 grams, and that would give you the answer. So the way you do a percentage is move it over 2 places and make it 0.113. So 0.113 times 27.8. And you get 3.14 grams of carbon. That's one way you could solve this. Another way to solve it would be exactly like I said before with a ratio. You could say 11.3 is to 100, so that would be the percentage ratio, because it's a percent, so it's out of 100. So 11.3 is to 100. 11.3 would be the carbon, so x, the grams of carbon, compared to 28. So the 100 is the whole thing, the 27.8 is the whole thing. The 11.3 is the carbon, the x is the carbon. So you could cross multiply, you could divide and multiply, however you know how to solve the algebra. The other way that I show how to do this then is you can do part over the whole again, but instead of multiplying by 100, multiply by the number of grams. It's essentially the same thing as the ratio. So the part would be 12. The whole thing was 106 right from here. And then times 27.8 grams. Any way we do it, the answer is going to be 3.14. So 3.14 grams. All right, next question. So now we jump into our first empirical formula question. A 1.349 gram sample contains chlorine and oxygen. So 1.349 grams contains chlorine and oxygen. On the quiz, I worded this a little different. I said an oxide containing oxygen, or I'm sorry, chlorine. A similar way to do this, though. The mass of just the chlorine is 0.6024. So if I subtract the chlorine out of the chlorine and the oxygen, I will get the first answer, which is how many grams of oxygen. So I have 1.349 divided by 1.349 minus 0.6024, and I get 0.7466 grams of O. So there's how many grams of chlorine I have, how many grams of oxygen I have. The second part of this is, what's the empirical formula between the two? So we have 0.6024 grams of chlorine. We have 0.7466 grams of oxygen. In order to find an empirical formula, I need to find the mole ratio between these two substances. So I need to divide them by their molar masses, atomic masses, whatever you want to look at it. So we have 0.6024 divided by 35.5 or 35.45 if you want to extend it to another significant digit. I like to keep an extra one there so you can see 969. You could even keep the 969. 0.7466 divided by the mass of oxygen, which is 16, 0.04666. Notice I'm keeping extra significant digits. Well, actually, no, I'm not on this one because we have 4 and 4, and I kept 4. So at this point, we have to find the ratio between these moles. So this would be the moles, but we need a whole number ratio. So the way we find the whole number ratio is divide them both by the smaller of the two. So I divide them both by 0.1697. This is going to give me a 1. That one divided by 0.01697. And I get a 2.749, which is essentially 0.75. So we learned that that's 3/4, and so I have to multiply that one times 4. I can't just round it. This is the thinking step. I have to, at this point, either have a whole number ratio, in which case I'm done, or one of those decimal equivalents, or really close to it. As you can see here, 2.7497. So that's essentially 0.75. So I have to multiply that one by 4. If I multiply that one by 4, I must multiply the other one by 4 as well, so that I keep the ratio the same. So that times 4 is 11. So the correct formula here is going to be Cl4O11. So Cl4O11 is the right answer there. All right, next one, another empirical formula. This time we have percentages. Our preliminary step whenever we have a percentage problem is we have to assume we have 100 grams of this, because we don't know a conversion from percents to moles, but we do know grams. So if I have 100 grams and 43.5% of that is phosphorus, that means I have 43.5 grams of phosphorus and 56.5 grams of oxygen. Now I have grams. I want, just like in the previous problem, moles so that I can do a ratio. So I'm here dividing by the molar mass of each. 43.5 divided by the mass of phosphorus, which is 31. I get 1.403. Again, keeping an extra significant digit there. 56.5 divided by 16. 3.531. Again, an extra significant digit. So this is, again, the mole ratio. But I want a whole number reduced mole ratio. So divide them both by the smaller number of moles. 3.531 divided by 1.403, and I get a 2.51. So just like before, this is our thinking step. It ended up a 0.5 this time. So in a 0.5, I have to multiply them by 2. And so I get a 2 to 5 ratio. So the correct formula then for this one is P2O5. P2O5. All right, the next question is a molecular formula question. So empirical is the reduced whole number ratio, whereas the molecular is the actual ratio between the atoms, not necessarily the reduced ratio. So NO2 is the empirical. So my choices here would be, if it was only one of these, NO2, it could be N2O4 if I multiplied it times 2, or times 3, or times 4, or times 5. But we don't want to just do random numbers. We're going to use that mass right there. So we know out of these, the correct one has a mass of 92 grams per mole. So what I do is find the mass of this one. So I have one N and two O's. So 16 times 2 is 32. That gives me a mass of 46. So I say 46 times what number equals the mass of the molecular from the problem. So carry it over to here. X ends up being 2. And so I know then the correct formula is N2O4, multiplying each of the subscripts in the empirical formula by 2. Okay, next question. A 10-gram sample of hydrated calcium chloride. So herein comes what I kept stressing about the vocabulary. What does it mean to be a hydrate? Well, a hydrate is a substance, in this case CaCl2, bonded weakly to so many water molecules in a certain mole ratio. So a 1 to 1, 1 to 2, 3, 4, whatever mole ratio of water. The way I find this out is I measure the mass of this whole thing. It says this thing weighs 10 grams. And then we heat it. And then when you heat it, the water goes away. So you are left behind with the substance called now an anhydrate. So it goes from a hydrate to an anhydrate. All right, so how many grams of water? Well, I take the grams of the CaCl2 and the water. It says the dry CaCl2 is 7.55, so I subtract those two, and that's going to give me the grams of water. So 2.45 grams of water in this substance. So then what is the percentage of water? Well, the percentage of water, just like we did in those other problems, part over the whole times 100 equals the grams of water over the grams of the entire thing times 100. And so that's, again, pretty easy math there. 24.5% water. So the part of water over the mass of the whole thing, again, the two added together was 10 grams. And then the formula. So the formula is, we got to find now the mole ratio. So I take the grams that I have of the calcium chloride. Most common mistake here is using the wrong number there. I want to use the anhydrate, just the substance, the calcium chloride, and it's 7.55. And the water, 2.45. So from there, I'm going to divide by their molar masses. That's 111.1. This is 18. 7.55 divided by 111.1, 0.06796 moles. Again, keeping an extra one. 2.45 divided by 18, molar mass of water. 0.1361 moles. Here's our thinking step again. I have to divide by the smaller one, which ends up being this one, and it should always end up being that one in the problems that we're doing. So now I'm dividing by 0.06796 into the moles of water. And now comes our thinking step, just like in the empirical formula questions. It has to end up a whole number ratio here. If it doesn't, something's wrong. Now, in a lab, there's error involved, but in these problems, if this does not end up a whole number ratio right there, you mess something up. Most likely, the molar mass. If there's an issue other than that, then I probably wrote the problem wrong. But I do tend to check this to make sure that's not the case. So then to write the formula, I am going to write the 1 to 2 ratio that I just got here. And then the name is calcium chloride dihydrate. So the fact that there's 2 means di. I use those same prefixes that we used for naming molecules. All right, so a hydrate contains 4.0 grams of YbCl3. There's a new one for you, ytterbium. I already have grams, so this one's a little easier. I can just go right to that last step, which is I have grams of the substance, I have grams of the water, divide by the molar masses. We're going to need a calculator for that one. So 35.5 times 3 is the chlorine. Let me look that one up. YB is a strange one. pretty much you're not going to come across any YB in your travels. So the molar mass, it is, I can't see my periodic table, 1 second. It is number 70 on the periodic table, and it says 173.04. So plus 173 gives us a molar mass of 279.5. What kind of crazy person uses ytterbium in their problems? All right, so now we have to divide 4.01 by 279.5 to get moles of that one. So we get 0.01435 moles. 1.55 divided by 18. So again, just finding moles. 0.08611. Smaller one. So divide that by 0.01435. And I get a 6. So again, there's the thinking step. It should end up a whole number ratio. If it does not, you mess something up. And with ytterbium, that's definitely a possibility. All right, so we have ytterbium chloride dot 6 H2Os. Remember, on your quiz, I'm going to name, or on your test, I'm going to name that first one for you. So I would tell you ytterbium, Roman numeral 3 chloride. It does need a Roman numeral. And then you would do the hexahydrate portion. So hexahydrate. All right, last few questions here. Another hydrate question. A hydrated sample of calcium sulfite. So calcium sulfite. So we know that the calcium sulfite and the water hydrated is 23% water. So my preliminary step, whenever I'm given a percentage, is I'm going to assume I have 100 grams of this. Because if I do that, I know how many grams of water I have. So then I have to subtract from 100 to figure out how many grams of the calcium sulfite I have. So hydrates are 2 parts. 1 part water, 1 part the anhydrate, which is the compound. This really got some of you on your quiz for some reason, and it was worded just like this. You started breaking this one into pieces and converting like an empirical formula. No, you do the whole mass. So we're dividing the 23 by the molar mass of water. Let me grab my calculator again. So 1 calcium, 1 sulfate, or sulfur, and 4 oxygens gives us a molar mass of 120.2. So we have divided by 120.2. So we got 79 or 76.9 divided by 120.2. 0.6398. Again, keeping an extra digit. 23.1 divided by 18. 1.283. That's going to give us a 1 divided by 0.6398. And we get a, I missed the 3 in there. So 1.283 divided by 0.6398. And it comes out to be 2.005. So again, there's the thinking step. That's why I knew up here on my calculator I must have messed something up, because at this point it should have been a whole number, and it wasn't. But you can see what I did there was when I divided, I tried to go too fast there, and I messed up the number that I should have been dividing by. So the correct answer here is CaSO3 dot 2 H2Os. It's a dihydrate of calcium sulfite. All right, now percentage. So another percent question. Percent equals part over the whole times 100. So the whole thing is going to be the mass of MgCl2 and 3 waters, and then the part is going to be of just the water itself, because we're looking for the percentage of water. Mg 24.3 plus 2Cl 71. So this thing right here has a mass of 95.3. Water we know is 18 because we're doing those hydrate problems, so we could just multiply that times 3. Oops. 3 times 18, which is 54. If we add those two together, we get 149.3. So the part of water over the whole thing, and then times 100. So we have the percentage equals 54, the part of water, over the whole thing, and then times 100. So 54 divided by 149.3 times 100, and we get 36.2% water. So this particular substance is 32.6% water. All right, so now that we're getting more involved with chemistry, we're getting the math down, we're getting moles down, we're going to start, doing much more reactions in chemistry as we start tomorrow with balancing equations and things. And we need to start focusing into that when we are doing labs. So we did a hydrate lab this week, but we also burned some magnesium last week. And I gave you the steps that we used and then the chemical reactions involved when you burn magnesium. So the first thing we did was we lit it on fire in the crucible. So we heated it really hot with the Bunsen burner. And these were the first two reactions that occurred. And so I told you what we're trying to do is get all magnesium oxide. So we're trying to purify the magnesium oxide from this first reaction here. And to balance that, again, we're going to learn balancing equations tomorrow. But that would be the reaction we want. Now, if that worked out right away nice and easy, then we'd be finished. But it doesn't because magnesium burns so crazy hot, you get this side reaction that occurs. And I just wrote down the wrong subscript there. That should be a 3 because magnesium. So we get magnesium nitride. So Mg3N2. So then we need a 3 there to balance that. So that's what happened first. Then we took these two, which are, again, we're doing this in a crucible. So that's what's left inside of the crucible now. There's no more magnesium. It reacted with these two gases when you burned it to produce these two solids. So then we want to purify the MgO. So we want to get rid of this. So what we did inside the crucible next was we added water. So we added MgO plus water, because that's in there when you added it to the solid. And we did Mg3N2 plus water. Remember, this is the step where we wafted. We wafted the gases. The first reaction here gives you magnesium hydroxide. The second reaction gives you magnesium oxide and NH3, which is ammonia gas. The first reaction is already balanced. The second reaction, let's see, it looks like we need a 2 here to balance the ends. That gives us a 3 there and a 3 there to balance the O's and the H's. All right, so there was the second reaction. So now inside the crucible we had these two solids because ammonia being a gas, and that's what we were wafting and we smelled it. All right, so then the last of the steps was now in our crucible we have this solid and this solid. Well, this solid we want. And when you heat up MgO, you just get MgO. So that one's already purified. But when you heat up magnesium hydroxide the last time, it produces magnesium oxide and water. And so that's already balanced. And so now left in our crucible, because we're heating it with a Bunsen burner, so again the water will be evaporated away, we have purified our magnesium oxide, and those are the steps that we followed in our lab last week. And so tomorrow on your test, I am going to ask you for these 6 balanced chemical reactions. All right, so there it is. Good luck.